Hello, I'm Laura Lewis. Welcome to class on covalent bonding. So this is part of GCSE chemistry. This is for all exam boards. So at Excel, AQA, OCR, and others. So you could all be asked about covalent bonding in all of those exam, or even international baccalaureate also as well. But it's mainly at GCSE. Okay, so I hope you find the video useful. Thank you for joining. So let's have an overview of what we're doing in this class today. I've been just going to remind myself, distracted by looking at me. Okay, so number one, an overview of how covalent bonds are formed by the sharing of electrons. Number two, a demonstration of dot and cross diagrams to represent bonds. Number three, an explanation of the formation of different simple molecular substances. A bit of a tongue twister, I didn't quite realise a tongue twister that was. Okay, next thing. So, yeah, covalent bonds are the sharing-caring bond, unlike ionic. So ionic was the business transaction, if you watch that video, between I want to sell my electrons, someone else wants to buy them, or there's giving and taking of electrons. So that was for the metals and the non-metals. Okay, so things like magnesium would bond with oxygen, aluminium would bond with chlorine, and such. This is for the non-metals. Okay, so the non-metals can actually chemically bond and join together, but they join together in covalent compounds. So hydrogen atoms. So hydrogen's only got one electron. Okay, sort of orbiting. So the most stable it would have two. Okay, most stable. Also, lots of hydrogen. It is like a sample of hydrogen atoms in the atmosphere. There's lots and lots of hydrogen atoms. There's millions of these things. So it's very easy for them to find another one or another hydrogen atom. They both want to have a before after shell. So what they do is they share a pair. Okay, they actually share a pair, and they kind of orbit each atom at different times. They kind of go like this motion, but we represent it by joining it, crossing over, and a dot and a cross. This is a dot and cross diagram. So the electrons of one element there's a cross, and of one atom, so they're both the same element, one atom or a cross, another atom or a dot. In reality, they're both electrons, they are the same thing, but we represent the dot and the cross to show that they are bonded and the electrons belonging to two different atoms. Okay, so yeah, non-metal ions, again, if you want to refer back to ionic bonding, the non-metal ions tend to gain electrons rather than lose, because metals tend to lose, if you revise that bit, and to fill their outermost electron shells. Most of the time they want to gain them. So neither atom can lose electrons, they don't want to lose any, so they both fill their outermost electron shell by sharing. This is called the covalent bond. Okay, so they share. So nobody loses any, they all share. Okay, so molecules, so these are simple molecules, simple molecular, forming single covalent bonds. So a single covalent bond is formed when atoms share one pair of electrons. So hydrogen, we want one more. Chlorine wants one more because there's 7, it wants one more to fill its outer shell. They just share a pair of electrons from hydrogen chloride, one hydrogen, one chlorine, hydrogen chloride. Water, very familiar to us, okay? So we've got hydrogen both wanting 1 each, and oxygen wanting 2 by itself. So we have 2 hydrogens, okay, either side. They're both sharing a pair, so they're both sharing 2 each. A pair obviously means 2, okay? And they're both sharing two electrons there. Methane, so these are all simple molecular. So methane, so one carbon. So carbon's got 4 electrons in its outer shell. So carbon, you've probably heard of carbon-based life. So most life on Earth, actually all life as we know it on Earth, not saying you've got never discovered any others, all life as we know it on Earth is carbon-based. So all of our reactions in our bodies are based on carbon reactions, lots of them are covalent. So it's actually a very important element here. So by weight, we're mostly carbon. So when I say we, are all living things. So animals, plants, fungus. Okay, yeah, obviously anything like that, we're all bacteria. We're all carbon based. By a number of atoms, we're hydrogen, but by weight, carbon. That's why we call carbon based. Everything's based around how carbon reacts. Okay, so carbon's got 4. It can share with lots of things. That's why. So it wants 4. It's got 4. It wants 4 to form 8. It's full outer shell. So it bonds with 4 hydrogens. Okay, so it bonds with 4 hydrogens. So they each form a pair and will share 1 pair of electrons there. And lastly, ammonia. Probably know it as not smelling very nice. Ammonia. Nitrogen's got 1, 2, 3, 4, 5. It needs 3. So it bonds with 3 hydrogens to form ammonia. Okay, so next slide that would be a good thing to do would be for you to just pause the video and then write down and draw your own covalent bonds here, because the more you write it, the more you draw it, the better you remember it. Okay, so most of the time things are learnt like that is the more you do it, the better you are at it, because lots of students don't believe they can do it. And I said, well, if you wanted to become good at playing guitar, what would you do? Like, everyone's like, well, you'd have guitar lessons and you practice guitar. Oh yeah, so you need to practice chemistry as well, and you'll finally get better at it. Okay, so because yeah, actually, I was at school, I didn't think I was that great at chemistry, but yes, it's just practice. Okay, so yeah, I just practiced it. Okay, and now I teach it a lot, so it's just all practice. Okay, so double covalent bonds. So double covalent bond when 2 atoms share 2 pairs of electrons. Probably guessed that. So you've got oxygen atoms here, 2, 6. It means their electron configuration. We're only showing the outer electrons. That's a good point here. Only the outer electrons are shown. So 6, they both want 2. Okay, so if they share 1 pair, they wouldn't have full outer shells. The easiest way of doing that is to actually share 2. They've got 1, 2, 3, 4 in this, 5, 6, 7, 8. Okay, and same over here. So in effect, they both have full outer shells. And in nature, oxygen actually does kind of float around like this in pairs, called O2, the O2 molecule. Yes, like the phone network. O2 molecule. Okay, so also other compounds of different elements can be formed. So carbon again wants its 4. Oxygen wants to share 2. Another oxygen wants to share 2. They have 2 sets of double bonds here. So the carbon dioxide molecule. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this effect they've all got 8. So when you're drawing them, make sure that they all have a full outer shell, otherwise that bond won't happen. So again, the best way of doing it is to copy those down and to draw them yourselves and check back, see if you're correct. Okay, and the only element really to do this is nitrogen. Okay, but it does it very well. Okay, I always remember this. Always remember this because it's triple. It's quite a unusual triple bond. So 2 nitrogen atoms, both have 5 electrons in their outer shells. They both want 3 extra ones. So what do they do? They share 3 pairs. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, so they effectively got 8. Okay, the triple bond. The triple bond is the strongest, and the more electrons they share, the stronger the bond. Okay, so the N2 molecule in the atmosphere. Okay, nitrogen is the most common gas in the atmosphere, and it bonds very tightly to another nitrogen. And you may know from the nitrogen cycle, you may not have done that yet at school, the only way to separate a nitrogen, or the N2 molecule, from another nitrogen is lightning. Okay, so it needs actually such a, in nature, humans have got ways of doing it with electricity, but the only way of doing that in nature is if lightning splits these. It needs so much energy to split this bond. Yes, that lightning has to do it. And again, best way to do it is to have to pause it and then to draw it yourself. Okay, bonds can be represented in other ways. Okay, and then this is a dot and cross diagram. Always remember that's called a dot and cross. You'll be asked that in an exam to draw a dot and cross, pretty much guarantee. Okay, so this is a stick diagram. Okay, this is kind of drawn without the. You may see some books. Okay, drawn without the circles, the same thing without circles. And this is called a stick diagram or ball and stick diagram. So all of the molecules we've seen so far are simple molecular structures. So it's only formed with a few atoms. If you go back, the they're not formed of more than about 5 atoms, okay, only a few. So in a container there may be several thousand simple molecules. So yeah, in a glass of water, several thousand simple molecules. The covalent bonds that hold the atoms together are strong. So the ones that hold them actually together, but the bonds between each molecule are weak. Okay, so they're strong here, but between the actual molecules are weak. These are called intermolecular forces, so they're between molecule, intermolecular. Okay, so a substance will allow electrical current to pass through if there are charged ions present. Nothing has got a charge here, so covalent substances don't have charges, so they do not conduct electricity at all. So simple molecular covalent structure, their full name, do not conduct electricity at all. Okay, so water, pure water, does not conduct. The reason why people say it's very dangerous, you don't often get very pure water. Water from a tap or from anywhere that's not a scientific laboratory as a distillation apparatus is not pure water. Okay, it's often mixed with things like salt and other things, and that will conduct. Okay, so if you sort of see the video on ionic, if something ionic is dissolved in water, it means that the whole solution will conduct. Okay, so when you boil a covalent substance, you're actually breaking the intermolecular, so the forces between the molecules. And as they're weak, simple covalent have low boiling points, and they also have low melting points. Think about water, okay, and think about like an ice cube, and think about salt. So it's so obviously that water will melt 0 degrees, okay, and it will be a liquid state just above 0. Salt, you'll have to really heat that up when you to melt that. Okay, so the salt is an ionic structure, the water is simple molecular. Lots of simple molecules are already gases, so if they're already a gas, that means that their boiling point must have been lower than room temperature. Okay, so you can actually have a negative, say something can actually boil at like -20, okay, or lower. Okay, so they will have very low boiling and melting points, simple molecular. So we can look at some models of simple molecular systems. So a model we get is a simplified way of showing something. So it doesn't represent something perfectly. Okay, so it's our example, if you made a model of your house, okay, not every single thing will be represented in a perfect manner. Okay, obviously it'll be a lot smaller, but if you made an exact clone, I mean, if you made an exact clone of your house, it wouldn't be a model anymore, would it? It would be an exact copy. Any word model means it's not exactly the same, a model. Okay, it's a bit like saying, yeah, a model plane, isn't it? It's not the same as a real plane. It's got similarities. The scale could be the same. The wings could be the same scale as the length of the plane, but there wouldn't be obviously the same engine and things like that. So you can sort of think of it as well as about the underground. So it's quite a visual one, where in reality underground stations are actually scattered around like this. Okay, we use a model, so in a map you can buy and download for free off a Transport for London. Okay, and look it up if you want to. That you can download this map, and this map is a model of this real representation. And this helps us to find out where trains cross. Okay, it's much neater, isn't it? Much easier to look at than that. It helps us to find out how to get from place to place. So models are there to help us to understand, rather than represent the true system. It's there to help us to understand something. Okay, so you can probably see that yeah, it's quite interesting actually that places on here, sometimes you think, if you look on here, you think, oh, okay, that's near somewhere, and it's actually a long way away. Or sometimes you think, oh, that's really far from another place, but actually you can walk it. Okay, sometimes a little bit of local knowledge or getting another map might help you. If you go to London and walk around, you may obviously benefit from another map, because yeah, these aren't true distances here. I found that out a few times. Okay, so I've got the 2D ball and stick model. You may have seen this nice drawing in books of ball and stick. So advantage shows which atoms are bonded to each other. Yep, the little line means a bond. It does not show true shape of the molecule. Methane may not be shaped quite like this, methane. So it shows the angle of the bond is 90 degrees. In reality, it isn't. Okay, so these could be differently placed in real life. It doesn't show how electrons are shared, and yeah, it doesn't show electrons. It just shows there's a bond there. It doesn't say what's sharing what with who. That's it. So dot and cross diagrams. So yeah, these are the ones who most commonly come across. Dot and cross. Yeah, well, remember they only show the outer electrons. Okay, so dot and cross showing outer electrons of circles. Don't tend to involve the inner ones. Sometimes you might start by drawing inner electrons, but then you end up just drawing the outer. So good way, it shows how electrons are shared, so advantage. Shows how electrons are shared in the covalent bond. Negative or drawback, gives the impression electrons from the atoms different. Yeah, we said that, I mentioned that earlier, so they're not actually different. So in reality, all electrons are identical. Yep, shows the electrons at a fixed position. Yep, in reality, the electrons are constantly moving, but on average maintain a similar distance from the nuclei of atoms. So yeah, in reality, these are actually obviously orbiting and moving around, but so it's shown on a diagram. That so just saying what compared to actual life, isn't it? Is that in reality that they're moving around, but obviously we can only draw them in a fixed position on paper. Shows the bonding angle is 90. Yeah, we've got probably the bonding angle, but we'll discuss that in a moment. So that's dot and cross. Oh. So the 3D ball and stick model. So this is sort of an extension of the 2D one. So in this one, you've still got the ball and the stick, but it's three-dimensional. So this hydrogen's coming out of the page, and that hydrogen's going away. You can't take a little while to get used to looking at those. A little bit of a taste of A-level chemistry, the 3D model. So there's quite a lot good about this one. It shows the actual shape of the molecule. Yeah, so it's 3D. Shows the correct bonding angle, yet you draw it with the correct bonding angle. But you need a modelling kit to show the true shape. That's true, because yeah, these again, we're kind of approximating. And you need something like a molymod, you may have seen. That doesn't show how electrons are shared in the covalent bond. Yes, there's no electrons there, is there? Okay, so so far we've been talking about simple molecular. Okay, just to show you what you have a giant structure. Just you think, okay, what's the other type then? You may be thinking, just briefly, okay, there'll be other videos on this. So giant covalent. So giant covalent, one example is diamond, okay, and graphite. So giant covalent formed of thousands or millions of atoms. These are truly huge structures. So diamond has got a tetrahedral structure, so that means that each carbon is bonded to 4 other carbons. All of the spaces are taken up. Very, very strong. Graphite has a hexagonal structure and is arranged in layers. So there's millions and millions, obviously it goes off for millions of atoms here, but they're on top of each other. Okay, so that leads to quite interesting properties. The diamond is very hard. There's very strong covalent bonds. Remember about bonds between atoms themselves are very strong. There are thousands of these bonds, so diamond is very hard. Nothing's really going to break them, apart from another diamond. The diamond's the hardest substance on Earth. Okay, only another diamond can scratch it. So to cut a diamond for some jewellery, you need another diamond. Graphite, we find in a pencil. They're both made of carbon, isn't it? How funny. Graphite is not as hard as diamond, but it's slippery. So if you look back, okay, these can slide over each other, and that's why you can write with a pencil. So layers of graphite slide from your pencil onto the page you're writing on. Okay, just to go over things, so to give you a little bit of a taste of a giant giant covalent there. So we looked at an overview of how covalent bonds are formed by the sharing of electrons. Looked at the representation or demonstration of dot and cross diagrams to represent bonds. They're the most important things at GCSE level. And then we looked at an explanation of the formation of simple molecular substances. So obviously we looked at all of these. These are all forming simple molecular. So these are all simple. I keep saying it, but it's very important. Simple molecular substances. Okay, so thank you for joining the class today. Hope you have learned something. It's good to go back and pause the video. You can pause me. Okay, sometimes. So thank you for joining, and I hope to see you in another class. Thank you. Bye.